So let's just do a recap. In case of massless pulley, if the pulley is massless, and let's say we have another rope on the attached to the center. Now, what is the property of tension force? Tension force always pulls the object, right? So if something is connected to this point, it will pull the object. So if you talk about the pulley will be pulled by the tension force. Now, if it is frictionless pulley, if you remember, so what is the property of frictionless pulley? In case of frictionless pulley, the tension will be same over the other side also, right? So while going from one side to another side, the friction force absence will make sure that the tension remains same. So if it is frictionless, then tension here will be how much? T only. Is this clear? Tell me, guys.
Yes, sir.
And if, because this is the new thread, so for every other separate thread, we have to assume separate tension force. So we can call this as T dash. And because it is massless as well. So if you write the laws of motion, Newton's second law, and the derivation of second law, what we know that net force equals to, this is not second law, but we can so from Newton's law of motion, we know net force equals to mass into acceleration. So for this pulley, the net force we can either write as T dash minus 2T or 2T minus C dash, right? If you're writing towards the right direction, this would be the net force. And if you want to add the net force towards left, you can add T dash minus 2T, it doesn't matter. So let's say the pulley is accelerating towards the right for some reason. Then the 2T is bigger than the T dash, that's why it's accelerating towards the right. So we can say 2T minus C dash, which is the net force, equals to mass of the pulley into acceleration. But as I said, mass is 0. And that's why the term on the right will be 0. So what you will get is 2T equals to T dash. And this relation will hold true only for massless pulley. Is this clear?
Yes.
So when a pulley is massless and frictionless, then you can write these relations. Okay. I hope it's clear. Okay. Let's do something more. So we have something called the Atwood machine. Now the Atwood machine is nothing but a regular pulley a regular pulley attached with, and it is suspended to some support. So you have to suspend from some support, and it is free to rotate, or at least it is massless. So you can do either thing. It is frictionless, massless, and or it is free to rotate it. And then with the help of two thread, which is passing over this pulley, you attach two mass of different value, you can say M1. If the hanging mass is different, then definitely the one of the block will go up, another block will go down. But that is not our concern as of now. As of now, we are only interested in what will be the tension diagram in this case, how to draw the tension force here. So M2 will experience tension in which direction, up or down? What will be the direction of tension force on M2?
Up.
M1?
Up.
Very good. So M1 is also up. So this tension force is representing the force of tension on blocks M1 and M2. What about the pulley pulley? What will be the tension on the pulley? And where we draw it? So tension on the pulley will be how much? Acting up or down?
Down.
So the same tension will pull it downward, right? And the value of tension will be same or different?
Same.
Same, because it's a massless and frictionless pulley. Okay. So this is called the Atwood machine. Then let's do something new. So now we have two masses, M1, M2. So what will be the direction of tension force on M1? Tell me, right or left or where? So for M1, the force will be?
Right.
Tell me guys, right. For M2? Rugve, tell me for
Upwards.
M2? Upward. Very good. And the value is going to be same or different?
Depending on masses. Different.
Will it depend on mass?
No, different.
Will it be different?
It's the same.
Same. Why same?
So because the string is massless.
Because the string is massless, it is passing over the frictionless pulley. Because the pulley is frictionless. And the same thread, the same string is passing over the pulley connecting both M1 and M2. So how many strings we have connecting M1 and M2? One or two strings?
One.
So in one single piece of string, how you can vary the tension if it is massless? So your string is massless, right?
Yes.
So for massless string, what's the theory? For massless string, the tension remains same as long as it is passing over smooth surfaces. Understood? So
Yes.
because it is passing over the smooth surface, tension will not vary. Only when you're passing through the rough surface, or if you're holding something, of course, whenever there is a friction developed between the string and the surfaces in contact, then the tension will vary on the two sides. It is clear what I'm saying?
Yes.
So in a single piece of string, you cannot have two tension. Is this clear?
Yes, sir.
So be very careful with the ideas, with the concept. Don't try to answer by your own intuition. Rather, try to answer it logically as per the theory. So when tension will vary, whenever there is a surface touching the rope, which is rough surface, which is having some friction. Is this clear, guys? Hello, hello, hello. It is
Yes,
clear?
sir.
Yes, sir.
Yes.
Sometimes you can hang the pulley with the help of a thread, because we know that we are not going to push, it is always going to be pulled. And now this is the, okay, unless I'm not saying explicitly that it is rough, you will assume massless and frictionless all the time. Is this clear? So every pulley you're going to assume as of now, massless as well as what? Frictionless. Unless I say that no, assume it's a rough, it's a massive. It's clear what I'm saying?
Yes.
Yes, sir.
Okay. Okay, I could have continued, but I don't have the space left. Now the assumption remains same if every pulley is massless and frictionless, and if I call the tension here as T acting on M2, can you write the tension in every other part of the string? So draw the tension everywhere. For every pulley, for every block, P1, P2, P3, you have three pulleys, P1, P2, P3. So draw the tension force for every pulley and draw the tension force for blocks as well. I have shown you one of the value. Can you write the other values? Do it. Okay, done, guys. Tell me. Look at this. If the tension is T for M2, the tension for the P3 will be T here and T here.
T. Yes, sir.
So how much tension will develop in this system?
2T.
2T, very good. And it will pull like this, 2T. And for P2, it will act like this, 2T. The same 2T will pass over this and will pull the support, but that's not going to move. And then how much tension will develop here on P2
40.
above? And then same will come to the M1 and understood. So knowing, okay, this is like a nomenclature. If you start with a T at the bottom, you can keep on multiplying the tension till you reach the top. If you start with T at the top, it will keep on dividing as you come down to the bottom. It will become half of the value you start with. Okay, if you go from top to bottom. So as a practice, it is always good to start from the bottom and go towards the top. It is clear?
Yes.
Yes.
Okay. So you can draw any diagram like this. So these all are numericals which we are going to solve, but to begin with, let's do it right. Rugved, are you getting it?
Yes, sir.
So we have a blank. And as we proceed, I will tell you the terminology that we use. So when you use a wedge, which is long, having some length like this, the word that we use is called plank. If it is short, we call wedge block. If it is triangular, we call a wedge. And if it is long, we call plank. Okay. So we have a pulley which is well supported to the surface ceiling, and let me make a hole here. So if I call the tension, if you call the tension on M as T, can you draw the tension everywhere else? For every pulley P1, P2, P3? And for the plank as well as for the block? Can you draw the tension for everyone? Tell me, guys. Can you do it?
Yes, sir.
Please go ahead. Tanu, this is laws of motion lecture. You want to attend? Hello, Tanu. Am I audible to you?
Yes.
Yeah, this is for laws of motion.
Okay. Okay. Sir. Then I'll leave.
Yeah, yeah. If you want, you can attend. Not any. Tell me, how's your preparation going on? What you're doing, like how many chapters you completed?
Sir, I have completed modern physics. And,
From the PYQs, you did the PYQs?
not all, sir, but I've done some year PYQs, 4-5
Okay.
years.
That's good enough. And
And electrostatics and magnetism.
okay. So that is from 12th.
Yes.
What about the semiconductor communication? None of this?
Semiconductor, I will do, sir. And then from
And
11th also some chapters I'm doing.
so from 11th, what you have finished so far?
Full kinematics, Newton's laws.
So I hope the tension force diagram is done. So T here.
Yes, sir.
For P3, it will be like T here. And T here, right? And so the Planck will be T here. Then T becomes 2T here. Correct?
Yes, sir.
Then 2T becomes 40 here. And then 40 here. Okay. So the whole idea is that you should always maximize the, always write the tension as per the rule. If it is massless, if it is frictionless, frictionless means the tension will be same on both sides. And massless means on the two sides, if all forces are collinear, or you can say parallel forces, on the two sides of the pulley, the tension remains same. That's the rule. Okay. Done, guys?
Yes, sir.
So for P1 and P2, so for the M1, we can draw T here. And you can easily realize that we have only one single piece of string passing over two pulleys P1, P2 and connecting all the three masses. So do you all realize this? It's a single piece of string passing everywhere.
Yes, sir.
Rugved,
Yes, sir.
do you realize this?
Yes.
And if you look at the arrow on the right of M2, a force F is acting there. So this is a way to say that someone is pulling this entire system towards right. And because of this pull only, the tension has been developed in all the other, can say strings. Okay. Once you know how to draw the tension force, your half job is done. The next you have to learn is how to draw normal force. Okay. So we know the normal force in theory. Today we are going to practice how to draw it. So what is the behavior of normal? Is it pulling behavior or pushing behavior? Tell me. Tell me, guys. What is the behavior of normal? What it does? It pulls or push? Tell me quickly. Come on. What it does? Tell me, guys. Come on.
Sir, pushes.
And how it acts? It always acts perpendicular to the visible surface, like whatever surface you can see. Okay. So in one line, I have discussed the origin of normal, but today we just need to know that how we should draw it and how we should understand it. Okay. So it is the pressing force acting perpendicular to surface and is always of pushing behavior. So we'll start with something very simple. Let's say we have a surface, a ground, and we have two blocks kept one over the other. So how to think of drawing the normal direction? We need to check for the contact force. So tell me, guys, for M1, how many contact force you can see? How many surfaces it is touching? Or it is being
Sir,
touched? One. And for M2?
2.
Very good. Excellent. So you can see clearly that M1 and M2 having different number of contact points. M1 is having just one. So who will apply the normal on M1? Who will apply? Which surface? Which surface will apply normal on M1?
Sir, M2.
The top surface of M2, isn't it? Hello, hello.
Yes.
And who will apply normal on M2?
It's the bottom of
Rugved?
M1.
The bottom of M1 and
The ground.
the ground. Very good. And what is the nature of normal? It is always acting perpendicular and it will press the object, right? So when you draw the something called free body diagram, that what we are going to do now, what we do is we hypothetically remove the two bodies So you can think this first body M1 as a separate body mentally. Now this is not we are doing physically. And why it is necessary? Because unless we are not going to do this, we cannot see the forces applied by one over the other. Once you do so, now you're free to draw the normal reaction. So how the normal will act on M1? Will it act upward, downward, and how? Tell me. So normal on M1 will act in which direction?
Up.
What will be the direction of normal on M1? How M2 will press M1? Up or down?
Upwards.
Upwards. And how M1 will press M2?
Downwards.
Downwards.
But because this is the action reaction pair, so the as per the Newton's third law, the value of both will be same or different.
Same.
It's the same.
So I can call N1. Let's call this as by name. So N1 for M1 is upward, but the N1 for M2 is downward. So in a way, M1 is pressing the block M2. M2 is pressing the block M1. But for M2, we have one more contact, which is at the bottom. So it will experience a new force, right? And the force on the M2 will be up or down. So the answer is definitely upward, right? And this force is a new force because it's coming from the different pair of contact. So we can name it differently. We can call N2. So as you will learn how to draw, you have to also learn how to name it properly. If you are not able to name it properly, it's difficult to write the equation. So we need to know how to name it properly. Definitely, if you want, you can also draw it for the bottom surface, which I have drawn here. So if you want to show it for the the ground, you can show it, although not required. So generally, we only represent for those bodies which are part of our system, which can perform some motion. But we can always do something like this as well. So this is the normal diagram, normal reaction force diagram for block M1, M2. This is actually called the free body diagram, but I'm just contributing the normal part, free body diagram. Later on, we are going to do the free body diagram in which all forces will be shown at once, not just normal, tension, normal, and whatever force you can see. So this is a very typical question which you will face at least 1,000 times in your life. So let's face the first time. Then 999 times you will face later on. So we have a block. Now the block is not kept on the horizontal surface, rather it is kept on an inclined surface, as you can see here. Just a moment. Okay, can you draw the normal for the block? and you are supposed to draw it properly, very clean. It should look as it should be, and then send it to me on WhatsApp. I would like to see everyone's answer. That's important. So do it and send it to me quickly in next 1 minute. Yeah, that's correct. Urugwet. Siddhant, you send me. Yeah, that's correct. Shreya, you want to send? Now I'll tell you something. Whenever you are drawing the diagram, okay, you make it more professional because you want to draw a normal. Draw exactly normal line, something like this. Okay. You can make it dotted line. That's also okay. And then you can draw the normal here. You can show it in, and this normal will act on the block of mass M. All right. And of course, if you want to draw the normal for the surface, which is not required, generally we write the force for the moving objects or for the objects which we would like to analyze, not for every other surface. So generally we see that. Anyway. So let's go back to the next diagram. Now this is called inclined plane. This is called and how we represent it. So to represent the plane, we can simply draw a line and we show its angle with horizontal. Generally, this is the trend. Sometimes we draw something like this. Okay. Oh, sorry, I drew the. This was your job. Okay. So we have two block. I mean, we have a block kept over a triangular shaped object which is called wedge. So this is the block. And the wedge is also having some mass m. So when we represent a triangle shape object, we can call it a wedge. And we are supposed to draw the normal for a block as well as wedge. When you draw it, make sure that you draw it by drawing the perpendicular properly. You should look perpendicular. Okay. So draw for the block and draw for the wedge. How to draw for the block and how to draw for the wedge separately. Okay. Draw it. So draw it and send it to me. Even when you're drawing the diagram, keep on thinking about the concept that why you're drawing this way. Because most of the time we draw it blindly. We don't think about why we are drawing, we just draw. I'm saying that no, don't just draw, try to think as well why you're drawing this. Okay, so that's correct diagram, Siddhant. But the thing is, if you draw this way, then so where is the normal for the block, Rugved? You haven't drawn the normal for the block.
Yes, sir.
Yeah. Okay. So there are some rules when you draw the diagram because you're supposed to solve it later on as a mathematical relationship will be obtained. Some linear equation will be obtained. So this is, if you draw like this, you won't be able to convert into mathematical equation with ease. So there are some good practices, and that practice you need to follow. Now the block is kept on a horizontal plane or inclined plane. Tell me how the block is kept. Inclined plane. Okay. So while drawing the FBD, while drawing the normal reaction for the block, you must draw the plane separately. Okay, so this is like practice. Some good or bad practice. You can say this is good practice. So first you draw the. So don't complete the diagram. Just draw the two inclined. I mean, just inclined plane with horizontal line. This way of drawing will give you the idea. This is the plane part. This is the inclined plane over which my block is kept. So here is my block. And once you have this block here kept, then draw the normal like this. This is the normal. If you are drawing this way, you may extend this line by drawing the dotted line, which will give you the a fair sense that it is exactly perpendicular. Make it as professional as possible. So when it comes to drawing the normal for the block, you must draw this way, and that's it. When you're trying to do it for the wedge, draw the wedge separately. So draw the wedge separately. I'm just shrinking it because of the space constraint, nothing else. And for wedge, how many points of contact you can see? Tell me. How many connection, how many contact you can see for the wedge? Tell me, guys.
Sir, two going.
Two. So one is due to the block, correct? And the one which is due to the block will be acting exactly at right angle. You may extend this line to make it more professional. It's at right angle. And this will be having the same name as before. It's N only. Why? Because this is action reaction pair. So we can't change the name here. But the other contact is with ground. And so it will act separately as this way. And because it's a different pair of surface, we have to name it differently N dash. We can't say everything as N. So whenever you're drawing the diagram in which the objects are kept on the inclined plane part, draw the plane part separately. Is this clear? Now the third thing you need to learn is drawing the normal for the curved surfaces. And this is very common when it comes to the chapter called circular motion. So we are going to face a lot of something like this. And here you need to remember the property of a circle. So for any curved surface, whether I call it cylinder, I call it sphere, I call it ring, I mean, of course, sphere, I mean cylinder. For any surfaces like this, the two-dimensional version of all such surface will be a circle. So although those things are three-dimensional, but when we draw the diagram, we draw it two-dimensionally. We just simply draw the circle. This circle could be a hollow cylindrical object. It could be like a pipe. It could be like a spherical object. It could be anything, but for us, it is just a circle. And in circle, you need to remember two properties. And what is that? The radius and the tangents are mutually perpendicular. Do you remember this fact? The radius is always perpendicular to the tangent. How many of you remember this fact?
Yes, sir.
So this is what you need to remember, nothing else. Because once you draw the tangent is called the instantaneous surface. Okay. And there are certain facts you can always learn, that if I draw a radius at angle theta from here, okay, the plane will make with horizontal the same angle. How we can prove this? So it's pretty easy. You can draw a line parallel to the vertical line. So this is also theta. And if this is theta, this will be 90 minus theta. So this will be again theta, right? Because this is 90. So from vertical, if you turn by theta, and if you draw a tangent, so remember that whenever you turn by theta from vertical, you draw a tangent, the angle of inclination of tangent with horizontal will be theta. You can do it with simple geometry if you want to do it. So is this part clear? Yes or no? The angle part is clear?
Yes.
So the angle made by the radius vector with vertical will be same as the angle made by inclined plane with horizontal. I hope this is clear. Hello, hello, hello. So to draw normal at any point on a curved surface, I mean, especially on a, you can say spherical, cylindrical or circular surface, you just need to draw the radius and extend this line. If I have kept some objects here, a tiny object compared to the radius, it's very small. The normal on this we can draw either like this, or you can draw here and you can draw normal like this. It doesn't matter. Sometimes we prefer to extend the line and make it normal because it's convenient to write, nothing else. Is this clear? So normal to the object kept on the spherical surface or cylindrical surface, or you can say circular surface ring. It will be along the radial direction. That's it. Is this clear what I'm saying? So how the normal will act? Along the which direction? So normal will always act. Tell me guys, normal will always act along the radial direction. Normal will be always radial, or you can say perpendicular to the tangent drawn at the point of contact. Is this clear? Hello, hello.
Yes, sir.
Okay. So if someone will ask you that there is a hemisphere, and this is the most important learning part for the other chapter like circular motion, you need to know how to do this. And if I draw an object somewhere here, a tiny block, let me draw just a dot itself. It's easy for me to draw. So sometimes block will not be there. You may have a ball kind of thing. And this object makes an angle theta with vertical. Let's draw this one. So what you are supposed to do is draw a radius. I mean, from center, draw a line, which is called the radial direction, and extend the line. So the normal is always perpendicular to the surface, and surface means the tangent to the surface. The tangent to the surface. And we know that the radial vector itself is perpendicular to the tangent vector. And therefore, this itself is the normal direction. So how to draw the normal? You can draw it like this. Or if you don't want to draw there, you can draw it here. It is the matter of convenience. There are not two. Let me draw it here. That's the reality. Later on, we will learn how to make it convenient in terms of drawing. So, so that we can convert it into a mathematical relation easily. So is this part clear? Hello, hello. Hello, guys. Is this clear?
Yes, sir.
So I hope you will be able to draw the normal. So now sometimes it happens that we have a spherical ball. So this is the famous stick and ball problem. So maybe the chopstick is, falling inside the ball. And I'll show you the center. Now the stick is touching the wall at 2 points, right? So can you see the surface of a stick end, or can you see the surface of the ball? What you can see? The stick end is like the pointed end, right? So whenever there is a sharp edge, I mean, there is something like a pointed end and the surface, a proper surface, you cannot see the sharp end surface. You can only see the surface of some flat surface. Okay. So you're supposed to draw the normal for the stick. Draw the normal for the stick. Understood what I'm saying? Hello, hello, hello. So
Yes.
can you draw the normal for the stick part? Let me make it more dark. So draw the normal. So first draw some thin line and then draw it. Okay. Do it and send it to me. I would like to see how you're thinking about the normal here. Yeah, good. So tell me why the the arrows are downward. Will it pull the stick or will it push the stick? What normal does? Pulls or push?
The stick on the spherical will be downwards and the ball
So you are
will.
supposed to, yeah, you are supposed to draw the normal for the stick, not for the ball. Like how the stick will experience the force. That is what you have to do.
So it will be reverse in the direction I did.
Yeah, just reverse the action. Okay. So that's correct diagram, but then you have to reverse the. So you are supposed to draw the normal for the for what? For a stick, no? So any line which you draw from the center towards the end will be the norm, will be the radial action, correct? So these are the radius vector, and now you can draw the normal direction. Like this. And we can call this as N1, N2. Why? Because these are two different surfaces, right? It is clear what I'm saying?
Yes.
So whenever it comes to the spherical surface, you need to draw the first radial direction, and that will be your the direction of normal reaction. So again, this kind of diagram you won't get in this chapter, but again, if you know this, then the next chapter after that is that's called the rotational dynamics. There you need to know all such things. Okay. So depending on the difficulty level, we come across in various other chapter, not necessarily this chapter. This chapter will give you a small glimpse of the world of particle dynamics, but later on you are going to study something called the rigid body dynamics. Yeah, there's something called rigid body. So there's someone trying to solve question there. You need to understand the various complex abilities. So let's say we have a floor and the the vertical wall, and I have a stick. These all are for rotational dynamics, not for this chapter, but it's good to learn at least once here. Can you draw the normal for this stick only, the pink one? So can you draw it? Just few questions. I mean, the purpose is to make you acquainted with the type of question you are going to face in future. So not all questions which you are solving here will be useful also. But this is the first step where you can form your base. You can understand better. Can you draw the normal here? Done this part. Yeah, that's correct. So that's right diagram for this part. So the normal will act normal to the surface, which you can see. See, you cannot see the surface of the rod or the stick, but you can see the surface of the floor or the wall, and that's why you have to draw normal to the visible surface. Whichever is surface you can see, draw the normal to that surface. So this is definitely the correct diagram. So what about the left part? Can you draw it there? Very good, Siddhant. That's correct. Very good, Rupert. That's correct. Okay. So for this surface, so one thing we have proved that you have understood this concept. So normal is always drawn perpendicular to the surface visible to you. Of course, we cannot see the surface of the edge of any surface, I mean anything. So we cannot draw it there. So that's the correct way of drawing it. Very good. So there is no end to it. This you can keep on drawing, but few more I'll draw here, and then we can stop. So we have the wall. So let's say we have a wall. So this is the wall. There's a wedge actually. And then there's a cylinder. So this wedge makes angle theta. Anyway. So you have a cylinder of radius r. That radius doesn't matter. So can you draw the ABD? I mean, draw the normal for the cylinder and draw so draw it and send it to me quickly. Yeah, that's correct for the cylinder. Look with, but if you're drawing the normal for any circular object, object with circular cross section, make sure that you draw the dotted line which is passing through the center, because it must be radial. So you have to draw the radial direction first, and you can draw the radial with dotted line and then complete the line for normal. Okay. So this practice is required. And again, if you're drawing the normal for the surface which is inclined, make sure that you draw the tangent there as part of the diagram itself. Okay, so that's a good practice. What does it mean is, if I'm drawing, okay, these are some practice you need to learn this. Okay, that we cannot draw the way we want. Okay, so one surface is vertical. So this is vertical, which is nice surface. Another surface is inclined surface, right? You can see here. So I must draw the inclined surface as inclined plane with the given angle theta. This is a practice, good practice. And once we are done with this practical, proper way of drawing the surfaces, then draw the normal. So the vertical will have the horizontal normal, that's for sure. But even this is not sufficient. As a good practice, you must extend the line and make sure that you show it that it is passing through the center. See, it's not exactly passing center. So I must draw a dotted line, and then I will extend this line and I will make it N. Similarly, to draw the other normal, I will first make a dotted connection with the surface. I'll extend the line and I'll call it, you can name change, you can say N2, you can say N1. And this is the right way of doing it. If you're not drawing this way, then again, you will face difficulty in explaining the mathematical part. So whenever you're drawing the normal for the surfaces which are not vertical or horizontal, you must draw the plane, inclined plane touching that point, and then draw the normal. Okay. So these are some good practices. Okay. So what about the wedge part? So it's not a big deal. The wedge part will explain the normal exactly in the opposite direction. And yeah, certainly it is at right angle. So make sure that this is right angle. And then you can extend one of the line. So you can draw this line. Like this, N2. Okay. Yeah, very good. So also, give the proper naming to the various surfaces of contact. So this normal we should call which name? N1, N2, or something else? Can we take the name N1, N2 again here? Yes or no?
No, sir.
Can we
something
use the
else.
name NO into here? Can
No,
we
sir.
use? Yes or no? Tell me. No. So we have to use another name N3. Okay. Why? Because it's a different pair of surface. I hope this is clear. Hello, hello.
Yes, sir.
Rugved, you understood how it is done?
Yes, sir.
Okay. Maybe the last question. This is called the edge contact, right? So a cylinder is touching the edge of two, you can say, rectangular wall. And let's say this is fixed. These are fixed concrete support, and you're supposed to do the normal on the cylinder, of course. So I want you to draw a very proper diagram which represents the correct way of normal. Okay? So you practice this, solve this, and send it to me. Make it as accurate as possible. It should look very professional and should match the way I draw. So try this out. Think about it. Done. Done.
1 second, sir.
Hmm. Correct. So also, okay, again, as a practice, always do the vertical line. Later on, you will come to know that this is how we draw the gravity. Okay. So sometime later we will come to know we have to also draw something called force of gravity, and gravity we always draw like this. So if I give you the mass as m, the mg will be drawn like this, but we are not drawing as of now. So that will be part of the complete FBD. You can always draw like this. So gravity always acts downward. That is what we add. Okay. So I think normal is pretty much okay. You know how to draw it. In different contexts, things will change for sure. Okay. So you're supposed to only understand the basic thing, and then as question will come, I hope you all can draw it with confidence. Okay, how to draw the normal, how to draw the tension force. Gravity is pretty easy. You can just draw a vertical line, and it always acts towards the earth center. That's vertically downward in most of the cases. So the next concept we are going to learn is called how to draw a spring force. And what is a spring force? Okay, as a concept. So before we try to understand the spring force, we'll try to understand what exactly is spring. So tell me guys, what do you mean by spring? No idea. So generally spring, when I say the word spring, what comes to your mind is a regular helical object, which you have seen in the a ballpoint pen, or maybe connected to the wheel of the you can say railway coaches. Okay, or you can say train, or you must have seen somewhere else also as a in bike. It's a shocker, you can say. In bicycle also we have the shocker or shock absorber, actually what we call. So you have seen this spring everywhere, but what is the definition of spring? And does it need to be this particular shape only? The answer is of course no. You can have a spring like this. You can have a spring like this. You can have a spring like this. So of course, you can have any shape also, and there is no rule for the spring. Certainly, we can call this as the helical spring. This is called the leaf spring. And these springs are connected in the, just above the axle of the trucks and buses. So the load of the entire bus is kept like this, and as it goes up and down, the leaves can open and close. This is called the spiral spring. So a spring is not defined by the shape, that is for sure. A spring must be something. Although we have taken the symbolic inspiration of the spring from the helical one. And so in most of the cases, if you read any literature, any text, they also use the helical spring as a symbol for spring. Some textbook will also use a zigzag kind of shape. But in all of this, what exactly is the spring? Is it the shape, or is it some other property which makes you a spring? So that is what we need to explore here. And that is what why we are studying this particular topic. So a spring is any geometrical configuration which is having the restoring capability upon deformation. So what you can define here? Any geometrical configuration having restoring capability. So any geometrical configuration having a restoring capability upon deformation is called a spring. So that is the spring definition. Now, what is the restoring capability? Which means if you deform, it will try to go back to the original, the shape, size, or dimension, the way it was earlier. If you're pulling it, pushing it, or in a way, if you're deforming it, it will try to go back to its original size once you remove that force. So that ability to go back to your original form makes you spring. So you can make a spring of anything. You can take a page, a normal page, paper, and you can convert this into a spring. So you can take a small piece of paper, just take a small piece. The rough page, you can take everyone. Taken?
Yes, sir.
And then fold it like this. You know how to fold this. Then, so you wrap it like this, like this, like this. So fold it like this. Make a small scratch. Keep on wrapping till you completely cover it. So this way, then this way, then this way, then this way. You know how to fold this alternatively?
Yes, sir. Yes, sir.
Yeah. So fold it alternatively, and once you're done, let me know. Done?
Yes, sir. Now.
Now, if you compress it and release, it will expand to a certain extent, isn't it?
Yes.
So put on a surface, compress it and release. You can see it's going back. Again, compress and release, it is again going back. Yes or no? Tell me.
Yes.
So you can see if you deform and once you release the force, it is trying to go back to the original configuration, isn't it? So this ability to go back to your original configuration when the deforming force is removed, that is called the spring. And it has come from the concept of elasticity. So now that is something which you will study in the last chapter of class 11, elasticity. But how we proceed is, we always try to deform something, and naturally it will have the capability of coming back to its original form. This ability we call spring. So spring is this ability. Okay, so when you have this ability, you are a spring, and you can have any shape, need not to be just like a helical, leaf, or spiral. It could be infinite possible shape, can convert you into a spring-like property. So now we have to study the types of spring. So in physics, there are two types of spring. One is called linear, another is called non-linear. Now in JEE syllabus, this is the JEE syllabus. We are only concerned with the linear spring. And as of now, we are not going to discuss or study about the non-linear spring. What is linear and what is non-linear? We'll talk about this. So a spring, when it is deformed, will create the restoring force. So any spring upon deformation develops a restoring force. As the name says, it will try to restore. So we call it a restoring force, which is kind of opposition to deformation. Now, opposition to the deformation means if you try to pull, it will try to pull back. If you try to push, it will try to push back. So it means whatever you do, it will oppose. That's why it's called the opposition to deformation. So the nature of a spring force can be both actually, right? So can we fix the nature of a spring? Is it pull or push, or is it both? Tell me, guys. The spring force will behave
So
as both
both.
force or only pull force or only push force?
So both.
Both. So when it will be pulling behavior? Upon elongation of a spring or upon compression of a spring? What do you think?
So upon compression,
Upon compression, it will be which behavior? Pull or push?
it will pull.
So when you compress, it will pull.
Sir, the other way around.
Yeah,
Wrong way.
correct. So any spring upon deformation develops a resisting force, which is kind of opposition to the deformation. We are talking about the linear deformation. Okay. So we will discuss about linear deformation only. So a spring is said to be linear if the restoring force developed is proportional to linear deformation, which means elongation or compression. So we have to only study two things. Either we are going to elongate the spring or we are going to compress the spring. Nothing else. We are not going to twist the spring. So as of now, we are not interested in twisting of a spring. Okay. So if you have played with the toys with keys in your childhood, probably now that's obsolete nowadays. But in our time, we used to have the toys which is, a key actually. If you turn the key and if you release, it will run for some time. And it is because of this, the spiral spring basically. So we should twist the spiral and then you should release it and it will unwind itself, and that will propagate the move the wheel of the mostly the car toys. Now we have battery driven car toys, so you can move it with remote control. So that's not using the, of course, spring. So a spring is said to be linear, said to be linear, said to be linear. If the resisting force developed. So the resisting force developed is proportional to linear deformation, and we are only going to consider either elongation or compression. Okay, there are two things which we are interested in. And linear means the force and the deformation will be proportional to each other. So more you deform, the more force it will exert. Okay. So symbolic notation. So our inspiration is basically from the helical spring. And helical spring is complex, it is everywhere. So the symbolic notation is you draw a helix. And for helical spring, we need to know certain more concept. So what is helical spring actually? So some so helical spring you can draw like this also. This is the two-dimensional view. Of course, this is the three-dimensional view. So you can draw the spring by any of these two notation. But I will particularly talk about the helical spring, some more detail, which you need to be aware of. So if you draw it properly, so a helical spring will be like this. So it's called end of the circle. So, okay, it's not nice diagram, but it's like this. So you can see in helix, when you make one rotation, So it's like one circle, and the circle is cut from here and it is stretched forward. So it's like the circle starts from here and it ends here. That is how we do the helix. So in helix, if you count the spacing, if you look at the spacing from the first peak to the second peak to the third peak, and so on, this spacing is called pitch. Okay. So between two successive, the coil tip, the gap is called the pitch. And in natural length, when you're not deforming at all, let's say this entire length, we can call it L naught. This is L naught, L naught. So we are going to talk about something called the massless spring. Our assumption is going to be massless. Okay. So this is the helical spring, and like you have the pitch length, and without deformation, the pitch will be same throughout. It means between any two successive coil, the pitch length will be same everywhere. I can say pitch length to make it more meaningful. So without deformation, the pitch length will be same throughout. But if you deform, then pitch length will vary. So now there are two categories of question. Are we dealing with the massive spring or massless spring? So there are certain key points which you should be aware of. For massless, now this is something really, really important. And that is our syllabus. For massless spring, upon deformation, every pitch will deform equally. So the final length of pitch will again be same throughout the spring. But for massive spring, the pitch length will vary throughout the length upon deformation. So as a theory, you must remember this. For massive, so for massive spring, initially the pitch will be uniform. Like without deformation, the pitch will be uniform. Without deformation, the pitch length will be same throughout. For massless and massive spring both. But upon deformation, when you're trying to deform it, the massless will make sure that the variation is same everywhere, but the massive will not follow the same principle. So for massive spring, the pitch length will vary upon deformation. Okay. Is this clear? So the three important key points, you have to just read it out and try to understand what is happening. So I hope this is clear. Hello.
Yes, sir.
Okay. So imagine if you have a spring which is fixed to one of its end. So we need to learn what is the property of massless spring in general. A massless spring is a really nice configuration in which if you apply force at one of its end, the force will transmit throughout the length of the spring without diminishing, which means the value of force, if you calculate at any end or any point, the answer will be same. What does it mean? So imagine this is the spring. This is called the natural length. Let's say we have n pitches. And let's call L naught equals to length of each pitch. So what is the natural length? So natural length of a spring will be how much? Let's call L naught. Can you say this is NL naught? You have n pitch. Each pitch is of length L naught. So what is the total length of the spring? The total length of spring without deformation is how much? Hello, hello. Are you guys not getting this? This is L naught. And we have such pitches, n pitch. So this is n number of times. Understood? So what is the total length of the spring?
NL naught.
NL naught. So this is called the natural length of spring, the length of the spring without deformation. So now what you do next? So you try to now here we are applying force. Slightly bigger. Now this new length is due to the applied force. This is called the applied force. Someone is pulling it. And now the pitch will disturb. So the new pitch, I can call it L naught dash. Or better, I can say only L. So what is the new length? L is how much? So L will be how much, guys? So this is the deformed length, right?
So NL.
NL, very good. So when you know the deformed length, when you know the original length, so it is very obvious to find the deformation. So deformation generally we represent by the symbol X. So what is the deformation? The change in length, right? And we only take the modulus because I'm not looking for the change. I'm looking for the change in value, not change in, I mean, bigger or smaller. So what is the modulus of change? So what is the deformation, guys? So can we write like NL minus NL naught? So the total deformation in the entire spring is how much? Tell me. Hello, hello, hello.
NL minus NL naught.
And therefore, what you need to understand that as you grow the pitch number of pitches, as the spring will become bigger and bigger, it will also suffer more and more deformation. So because the deformation is happening at pitch level. So as you grow the count of pitches, the total deformation will increase proportionally. Yes or no? So can we say X is proportional to N? Can we say, guys? Tell me.
Yes.
Yes, sir.
So a spring with large number of pitches will have more deformation for the same force. So keeping the force same, what do you think? If I keep the force F and if I decrease the length of a spring, the deformation in each pitch will differ or remain same. Oh, once again, my question is, I think you have not answered the question. Question is, imagine you are applying a force F, okay, to a spring of length half of this original spring. So you simply cut the spring into two parts and then again you apply the force F. What will change and what will not change? So the new pitch
Sir,
length will
length will change, but change in length won't.
So the total deformation will change. So if I cut into half, the total elongation will also become half from the previous case.
Yes, sir.
What will not change? No, this is difficult to realize. The individual pitch deformation will not change. All will deform by same value. So the property of master spring is the force applied at one end will transmit everywhere. Which means no matter where you cut the spring, if you try to understand how much force is developed here, the answer is F only. Actually, F is equals to, or you can say F is proportional to L minus L naught. That's it. The deformation of a single pitch is due to the applied force. The increase in the number of count of pitch will only increase the total deformation, but the force responsible for the deformation is same for every pitch. So as we decrease the length of the spring, nothing will change for every individual pitch. But because we have less number of pitches, so we will have less amount of total deformation. I don't know whether you are getting this point or not. It's really difficult. Are you guys understanding what I'm trying to explain here?
Yes, sir.
What is happening? the force you're applying even at one end, the same force is, in a way getting transmitted everywhere. So it's acting everywhere F on. So even if I create a spring with only one pitch, just one pitch long, and if you apply a force here, F, what I was trying to explain that this length will be exactly L only. It doesn't matter how big it was. So here the F will be proportional to L minus L naught. If I start with only one single spring pitch, single pitch. As the pitch will grow in value, then what I'm saying, as the pitch will grow, then definitely the total deformation will grow. So F is proportional to L minus L naught. Understood? Hello.
Yes, sir.
So here F equals to something called K dash into, let's call K dash, or let's call K naught, because this is for a single pitch. But if you do it for here, so here the F will be proportional to N times. And if I write this equal, what will happen? I have to write N K naught L minus L naught. And this N times K naught, we prefer to write as K. Sorry. Okay, my bad. This K naught, just a minute. This we can write as K naught N into. So we prefer to write this as K naught into X. So the deformation here itself is this much. We don't have X differently. So here with single pitch, the X will be also equals to the only difference is the X in a bigger spring will have more value, and in small it will have less value. That's it. But the spring the proportionality constant, which we are going to call later on, is spring constant, that will remain same. Okay, so the way we consider this, I will show you how we consider this. So of course here X is different, here X is different. Okay, what I can do is to compare this in a better way. Just so now actually we are talking about the linear spring. What is the property of linear spring? For any linear spring, that spring force, see now this is the applied force. What is spring force? Spring force is the force which is trying to oppose. So if you're trying to pull it right, the spring force will act actually left, isn't it? A spring force is not what you apply. Spring force is what is developed within the system. So for linear spring, the spring force is proportional to deformation. And whenever we equate with, and it is not just proportional deformation, it is always opposite of deformation. So if you try to pull it right, it will act left. If you try to push it left, it will act right. So we have to put minus sign. Now this is the vector expression. And because it's one dimension, so I'm not putting the arrow sign, because in one dimension, the plus minus is sufficient to take care of the vector nature. So we write FSP equals to some constant, and this constant we call it a constant of proportionality, but also called spring constant. So in different texts, it is called differently. So sometimes you can call spring constant, sometimes you call force constant, and sometimes we also call this as the stiffness of spring. Okay. So do you realize this? Now this is eventually when you write the spring force formula. So FSP equals to minus Kx. This is called the vector expression, or simply I can call vector form, but generally in scalar form or in value or in magnitude, you can just write FSP equals to Kx, where x is the modulus. You can say K mod of x or mod of SP. So when we are solving the numerical, we know x is the value. I will take x as a value and then I will solve the numerical. And I will not put the modulus and everywhere, but it is understood that if it is only about the value, it is always the magnitude of force. We know the direction is always of opposing behavior. So if you try to pull, it will pull back. If you try to push, it will push back. So a spring force can be of both behavior. It could be of pulling behavior as well as it could be of pushing behavior. So it will, spring force will be, you can just mention this quickly. So upon elongation, what is the behavior you can expect? So upon elongation, which behavior you expect? Pull or push? So how you elongate? You elongate by stretching, right? So you pull to elongate or push to elongate? What do you do? How to elongate a string? By pull or by push?
Pulling the string.
So when you pull the spring, it will also pull you back. So upon elongation, which behavior it will exhibit?
Pull.
Very good. So upon elongation, it will exhibit upon compression. What to expect?
Push.
Okay. So spring force is not acting for the spring, it is acting for every pitch. Every pitch is capable of developing or generating the same force as the whole spring will generate. Okay. All right. So I will do the 3 diagram quickly. So we have a spring, we have a block. And no. So someone is pulling this block by applying the force F. The block is connected to the spring, so by virtue of block moving towards the right, the spring is going to be pulled for sure. But once you try to pull the spring towards right, it will try to pull you back. So the spring force will act in this direction. Now we cannot say that the spring force and F are same. They are different. Spring force depends on how much deformation you have exerted so far. So let's say if the spring is in natural length, the block is connected and you start applying the force F. At the very instant, what will be the spring force when there is no deformation? So spring is till now not deformed. What will be the spring force? So will it be 0 or non-zero? Tell me. The spring is in the natural length. The block is connected to the spring. I am just applying the force F right now at this particular instant when there is no deformation in the spring. What do you think the spring force will be? Or
0.
should it be?
Zero.
So definitely it will be 0, because see, just because I have applied the force doesn't mean spring force will develop. Spring force will take some time to develop because it will only develop by virtue of deformation, and deformation cannot be instantaneous. It will take some time to get deformed. So that is why we call that spring force is only developing by virtue of deformation. So you need to wait for deformation. Okay. So right now it is 0 for sure. But after some time, what will happen? And now this is definitely in a state of deformation because this is the natural length. And we represent the deformation by a value x. As I said, the x represents only deformation part. Now the spring force is always going to be of opposite behavior, the pulling behavior in this case, or you can say because you're trying to deform by elongation, it will try to go back to the original length, and so the spring force will act in this way, right? Because what is the way to restore? How the spring force can restore its original length? And in order to restore, what you think? The force should be acting towards left or right? Common sense. How to restore? Common sense. How to go back to the original position? Common sense. How the spring force should act? These all are common sense. I mean, if you understand how you should act, you can answer it. So the spring force will act left or right on the block?
Left.
Are you realizing this part? Why it is acting left?
Yes. Sir.
So now because of the value, okay, what is the value of spring force? Just magnitude in magnitude. So it is simply K, which will be given to you of the spring into X. That's it. And if I go back to the same problem, and if I apply the force this way, And if I call this is natural, and as a result of this force, the spring looks this way. And now if you compare, as I said, I always take the value of deformation as x, not the length of spring. So you can call this as L, not you can call this as L. So my x is always the big minus small. This difference symbol means subtract the small from the big. That's why I don't write a minus sign. A minus means you subtract left minus right. That's it. But this means subtract whichever is smaller from the whichever is bigger. And in that way, the spring force, now this case, the spring force is going to act towards right or left. How the spring force will act on the block?
Towards right.
Towards right. And that's common sense, right? I mean, there is no formula, there is no magic trick. And we cannot say that FSP is same as F. I have no idea whether it is equal or not. Unless I'm not saying that they are equal, you cannot assume these are equal. So only at equilibrium, only at equilibrium, you know what is equilibrium? When net force is 0, right? Only at equilibrium, the forces will balance out each other, which means the applied and the FSP will be equal. In this case, of course. It is clear, guys? Tell me.
Yes, sir.
So a spring force cannot change instantaneously. A spring force can change when deformation will change, not what you apply. So what you apply will not determine the spring force, rather the deformation will determine the spring force. And this is a very common assumption that applied force do not determine a spring force, rather it is the deformation. So who decides the spring force? Deformation or the applied force? Tell me. Hello. So who will determine the spring force? It is the amount of deformation that the spring has suffered, isn't it?
Yes.
If you know the amount of deformation it has suffered, you can answer it. If you do not know, you cannot answer it. Okay. But under the condition of equilibrium, we can definitely answer a lot of things. So we'll look at the spring block system for equilibrium condition. Spring block system. So spring block system. So let's say we have a spring attached to a block. And the block is acted upon by a horizontal force F. Now F is the force acted upon on the block, acted upon on the block. Now the spring having the spring constant K, and eventually the block has gone somewhat right, and assume it is at equilibrium. So at equilibrium, for block, the spring must have some deformation. Let's draw the force diagram for the block. Okay. So F is the force applied on the block towards right. And if the spring has suffered some deformation, then the force that spring can apply will be left or right. How the spring will apply force on the block? Okay, first of all, you tell me, you applied the force F as per the diagram. What do you expect? Elongation or compression? Common sense.
Elongation.
Elongation.
Raghuver, tell me.
Elongation.
Elongation for sure. So it will go towards right. So the spring force will act in which direction? Right or left? On the block. So what will be the direction of spring force on the block?
Towards left.
Towards left. Very good. This is the spring force. And because this will only happen when some deformation has occurred, let's X be the deformation. So for equilibrium, what we can add, the net force must be 0, which implies the F on the right is equivalent of F on the left numerically. Correct? And F is given FSP, we can add as KX. So what is the X? Let's call X mean value. So at equilibrium, the spring will deform by value F by K, assuming the block is at rest or it is not accelerating. So rest is not required even if it is moving at mean position or at equilibrium position, the net force is 0. Okay, equilibrium doesn't mean the object must be at rest. It's again a very common misconception. So we have two types of equilibrium. Static and dynamic. In static, velocity is 0 and A is 0. But in dynamic, V is non-zero, although A is 0. But both are called equilibrium. And for static, it will be at rest. For dynamic, it will be moving, but with 0 acceleration. In both cases, you are free to write the answer F equals to Kx, F equals to Kx. This is correct for both cases. So if I say static equilibrium, then definitely it is at rest. So for static equilibrium, V is 0 and A is 0. For dynamic equilibrium, V is non-zero, but A is 0. Okay. So the word equilibrium should not confuse you. The equilibrium only means what is 0? So equilibrium means acceleration must be 0. So a position of equilibrium is not the position of rest always. I hope this is clear to all of you.
Yes.
So a position of equilibrium is not the position of rest always. A position of static equilibrium is the position of rest. But a equilibrium of, a dynamic equilibrium doesn't mean that the object is at rest. It is moving with some velocity, although the acceleration at that instant is 0. In both cases, you can write F equals to Kx, and X will have the value A by K. Sometimes equilibrium position is also called the mean position. Okay. So as a note, position of equilibrium is also called mean position. Okay, it's called mean position. Again, try to remember all of this. It is clear. So there are many key points you will come across as you study more and more laws of motion, and you have to get rid of your own intuition way of solving question. Rather, try to follow certain scientific methods, the definition, the law of motion, and as per the definition, the theory, the concept which you are studying right now, try to see through the problem through the lens of this concept and theory, and then only try to make some judgment, not what you feel about it. Because generally in this chapter, the biggest issue is of not having the command over the chapter, that you develop your own intuition in a wrong way. So try to avoid it. Don't try to develop your own intuition. Try to develop the ideas as per the concept taught. That's it. So if spring force is this, then think this way only. If you're supposed to learn the linear spring, think of the linear spring. If the linear spring says that it is proportional to deformation, follow it. It is proportional to deformation. F equals to kx, F equals to kx. F equals to minus kx is the vector notation. F equals to kx is the value-wise notation. So you have to be careful about every term, every symbol which we write, and the correct interpretation will lead to the correct result. If you get deviated from the theory, the chance of making mistake in future is very high. Okay. Sometimes we can use the spring with hang something. So let's say you have a spring and you have hanged a mass and it is at rest. So when something is at a rest, then it is definitely at static equilibrium, right? So it is at rest and it is at static equilibrium. You can say this is static equilibrium. So what do you think? The spring will be under deformation or will be in natural length? What do you think? What do you expect? Here the spring will be under deformation or in natural length? No idea.
So deformation.
And who is responsible for this deformation? Which force? Which force is responsible
gravity.
for deformation? It is gravity. So gravity is acting on spring or on the block?
On the block.
So gravity is acting here. As a result of this gravity, it will try to go down. But as it will go down, the spring will elongate. And as a result of elongation, it will create a counter force, Kx, in the upward direction. So there are some rules you need to remember. You're not supposed to leave the block instantly from the natural length. No. You hold the block, you raise your palm slowly down, slowly down, slowly down, slowly. And then you will see that after some time, your hand will go down, but the block will remain there. So it is called the slow release of the block. So you have the spring in the natural length, you have the block attached, then you hold it by your hand. You lower the hand level slowly enough. The block will go down, and eventually, even if you move your hand further down, the block will not go further down. That's called the equilibrium condition. And at equilibrium, at static equilibrium, which force will balance each other? So the block will be under the action of two forces, one the spring upward and other the gravity downward, right? And for equilibrium, these two forces must cancel out each other, isn't it? So can we write FSP equals to mg, guys? Yes or no?
Yes.
Because there are no other force, and FSP can write a kx. I'll put a m subscript because it's a mean position. It looks nice. So x mean is how much? What is the deformation under the gravity? At mean position, it is mg by k. Do you realize this part? Tell me yes or no.
Yes.
Hello, hello. Okay. Now you know this is the spring force. This is the, I mean, the block is at rest. What will happen if I cut the spring from here? And if I ask you that what will be the acceleration of the block immediately after cutting the string? So immediately after cutting of spring at A, what will be the acceleration of block? Just after, like not after a long time, just immediately, what should be done? What happened? See, to acceleration to have or not, you need to check whether the force has changed or not. Gravity will change because of cutting, yes or no? See, whether I cut the spring or not, what will happen to the gravity force on block? Will it change, yes or no?
Oh,
Now, what will happen to the spring force? When I cut it, And I'm not giving you any, delay. There is no delay. Just after cutting, what will happen to the spring force? Will it change? Yes or no?
Yes, sir.
And the answer to your surprise is no. When you cut the spring, actually the upper pitch will compress first and it will keep on coming down. And then the last pitch, the pitch next to the block will compress at the end. Actually, what is holding the block is the deformation in the pitch next to the block. And one pitch is sufficient to hold it back. So for that, I'll show you a very nice video called the Slinky test. Okay. Hopefully this will open your eyes. I have also performed this experiment personally, and it's very obvious. You can also do it. If you have a Slinky at home, you simply drop the Slinky and what else? Record with the slow motion camera. Like you can just use a slow-mo of the mobile phone and you will realize that it's pretty easy. Okay, anyway. So I'll go to just a moment. It's very old. It's very old. It's a more than 10-year-old video. Okay, can you see this video now? Tell me, guys, can you see this?
Yes.
Can you see the Slinky hanging from this, this guy, hand of this guy?
Yes.
You can also see the pitches of different length. So the top pitches are bigger and the bottom pitches are short, right? If you focus carefully, you can see the pitch length is not uniform. Because in reality, we can't have the massless spring. We have the massive spring. It will have some mass. So do you all realize this part? So this guy is very famous guy. It's having the YouTube channel called Veritasium. Okay, now look at this. Okay, now you can see that the top is falling, bottom is not moving at all. Do you realize this? The bottom is not moving at all. Check, check, check now. Bottom is moving. It's still. Now bottom will move. What you realize? Until all pitch will not deform and go back to the normal length, it means if every pitch will compress back to the original length, and when the last pitch, which is the bottommost pitch, when it will get compressed, then the entire spring will start coming down. So the bottom is not coming down. Do you realize this? Hello guys, am I audible to you?
Yes, sir.
Yes, sir.
You can see this. Watch it carefully. Is spring bottom moving?
No.
Okay, so you all can do this experiment at home. It's very simple. So what will happen if you cut the spring? This will start compressing from here to here, and only when it will come here, then the block will start falling down. Do you realize this? What I'm saying? Hello, hello, hello. Because the spring force cannot change instantly. It will take some time to change. So immediately after cutting the spring at A, the spring force remains the value it was earlier. mg will remain so, and because they were balancing each other out, so they will keep on doing so, and hence the block will have zero acceleration. How many of you have understood this part? So today you can do the slinky test if you have slinky at home. If you don't have, buy it. It will come in 10 to 20 rupees. Take a simple one, just drop it, take a mobile phone camera, capture the image in slow motion, and you can see the result. It's so simple. Okay. So I'll discuss more of this slinky problem. So the next lecture is going to be the spring block slinky problem, which is supposed to be the most difficult part of this chapter. But you will have no difficulty in understanding this. It's so easy. It is about realization, and then we can solve it. Okay. So see you in the next lecture with this slinky test problem. So we'll do much more than what we did today. So bye guys. This is the end of the theory part. We are normally now entering to the